Okay, that's good. I'll share. Hopefully, people can see my screen, right? Yeah. Yes. People can see my screen, right?
Yes, sir.
Yes, sir, it's visible.
Okay, okay, okay. Yeah, sorry, I didn't get a confirmation. So remember this question last time? Like people were asking me about, if there is an image of this size and a kernel of this size with a stride and a padding and all that, what is the resultant feature vector? So let's quickly discuss that once, very quickly. So let me, take a blank part and then do it. So we'll clarify that. It's a very simple formula. Okay, it's not a big deal. We can, and you'll get the intuition behind it. So let's say that you have an image of, say, 5 cross 5, right? Right. So 5 cross 5 image and a 3 cross 3 kernel. All right, and you're convolving this, and you want the resultant size of the feature map, right? Of whatever feature map that you're getting. Now, how you do this is, so you can do this in 2 dimensions, right? Like if you consider each, this to be the horizontal, sorry, the vertical dimension, and this to be the horizontal, right? Or rows and columns, whatever it is, right? Doesn't matter, right? So because sometimes the possibilities are the image isn't square like this, there is a possibility that the image is rectangular. So the number of pixels in the columns would be higher than in the rows, right? So there are situations like that. And what we can define is the output number of pixels, WH, is, so I'll put this symbol, I'll ask you what this is later, but that's nothing but, so your input image size, image, right, plus 2 times p, where p is padding, minus k, where k is the size of the kernel, by sh, which is stride, plus 1. Okay, right? So this is basically it. If you apply this, you'll get what the feature vector, so the resultant size of the feature map is. Okay, so let's take the simple condition. You guys help me. Okay, so now tell me one thing. Why 2 times padding? Why do you do 2 times p? Any idea?
You have to add her on the top and bottom.
Yeah, so you pad on both sides, right? Padding is symmetric. You do it on the top, on the bottom, or if you're doing it, if you're computing it for the rows, then you add it in the sides as well, right? So yes, so that's why 2 times. And then sometimes k can also have a subscript, depends upon the type of kernel you use. Most often than not, you will use a square kernel, right? So if you're using a square kernel, that is the rows and the columns are the same, then you don't have to worry about this. K is the same irrespective of whatever, which which side that you are choosing or which dimension you're choosing. And the stride
So
also.
please,
Mhm.
so please re-explain why there are 2 times padding.
So if you're padding it, you pad it at the bottom and also at the top, right? So for a given column, you'll have padding at the top and at the bottom here, right? So that's why 2
Any
times.
specific reason, sir, for double padding, top and bottom?
I typically you do that, right? Remember our
Yeah,
conversation
yeah.
last night? So if
But
I
any
show
reason
you
for
that,
any
reason
reason?
is to make it symmetric, right? Like so that the size does not get affected Let me, if I can dig back to that. Oops, sorry. Uh, where did I talk about this? Somewhere here. Ah, yeah, there you go. Right. So here we do padding on both sides. The reason being that at the end of the day, we want, for instance, in this case, the same size as that of the image. We wanted the output of the convolution. So we want to pad it on both sides. If you pad it just on one side, then you will lose this top row. So, and you will get an asymmetric feature map, or this feature map that's not, so you won't have this, right? Because you lose this part, and the kernel can't be placed on top here, right? So it can't be placed here. So if the kernel can't be placed here because there are no zeros that are padded on the top, then you would not get the same size as that of your image to be the output of the kernel.
In this diagram, like we are padded in both side, right?
Yeah, yeah, here
Both
and
side,
here and
four
here
side.
and here, all four sides.
Yeah, yeah. In that case, dimension will same.
Yeah,
Means
dimensions should be
it will be in the square format only.
exactly.
Otherwise, it will be become a like a rectangle format.
Rectangle, yeah, absolutely, you're right, exactly. Yeah, so that's why when I was talking about this formula, I mean, I lost it. Where did I do it? Did it at somewhere at the end here? Okay, yeah, yeah. So anyways, I'll write it again, doesn't matter, right? So the output of your feature map is this operation. I'll tell you what that is. The size of the input kernel plus 2 times padding minus the kernel size divided by the stride plus 1. Okay, so now let's take that scenario, right? Let's take that your image is 5 cross 5, all right, and then your kernel is 3 cross 3. Now I say that there is no padding, there's, you're not padding as well, and then you're not taking any stride, right? Now what is the output feature map size? So apply this logic. So now WH and WV, horizontal and vertical, are both the same because it's a square image, right? So you don't have to worry about it. So whatever you do with one computation is okay. So I didn't explain about this operation right yet. So anybody know what this operation is? This invert, this L?
Least integer function,
No. People might have
Clamp
seen.
function.
Sorry?
Clamp function.
It's also called something else. It's correct. What are you clamping? There's something called like this and something like this. Anybody?
Upper and lower bound, like if
Yeah,
it's
yeah,
like
yeah. What is it called?
floor and
Yeah,
seal.
very nice. Yeah, this is the floor function, and this is the seal. Okay, so that means that you. So what do you do when you have a flow function? So if you get a floating number, floating point number, what do you do with it?
You
Like
round it to the previous integer. Like
yeah,
if it's 2.35, then it's rounded up to 2.
Yeah, so you round down, right? You round down, and in this case, you round up. So floor of, as you said, 2.35 is
2.
two.
2.
okay, yeah, cool, right? So, but the same thing, seal of 2.35 is 3. Yeah, okay, got it, right? So the reason being that this ratios often might not give you an integer value, right? And you might get issues with that. So if you don't get an integer value, you need to figure out a way to map it to the closest integer. The floor function does that, and you add one more plus 1, and that will give you your kernel size. So for this input image and this kernel, sorry, the output feature size, yeah, for image and this kernel, what would be the output feature map? So where no padding and we're not taking any strides, or sorry, stride of 1. I'm sorry, not 0. Stride can't be 0. Stride of 1. That is, you're just moving one step at a time. Calculate this. So what is MH?
5.
Yeah. So
3,
5.
sir.
5 plus, there is no padding, 2
3,
times
0,
0, minus 3
3.
divided by 1, right? Plus 1.
How
So
we got
that's,
1, sir?
stride is 1, right?
Acha, oh.
Right? So that's 5
3.
minus 3, 2 plus 1, that's 3, right? So the output feature map size is 3 cross 3. And do we see this? We see this, right? Yeah. So
Sir, actually, I have one question.
yeah.
Uh,
Wait a
when I was
second.
going through LANet or some AlexNet, some nets,
Uh-huh.
so in that actually there is a kernel size, right, sir?
Mm-hmm.
Not like 3 by 3 number of kernels. How do
Right.
we determine the number of kernels? I did not
That
find.
number of kernels is determined by us, right? Most often than not, because those are parameters that we can set. How many how many
Okay,
kernels that you want, you can set it, right? That depends upon you. Because every time you set a kernel at this, so let's say this is one stage, you can take any number of kernels. If you remember, right? Like you can take any number of such kernels, and that will give you one such feature map that you want from the image, right? So that you decide. But the output's feature map size is decided by how the kernel interacts with the image, right? How the result of the convolution works out. So in this case, the output feature map size is 3 cross 3, right? So if you remember this scenario, right? So when we were talking about backprop, right? This is a 5 cross 5 image. This is a 3 cross 3 kernel, but we got a 2 cross 2 output. Now, how is this possible? Why is this a 2 cross 2 output? Anybody?
Sir, can you repeat?
So just now we discussed that we took a 5 cross 5 kernel. There was no padding, right? A 5 cross 5 image, 3 cross 3 kernel. But in this case, the output of the convolution is 2 cross 2, right? But we just figured out it's 3 cross 3 if you take this. But what has changed here?
actually in last class we did something there.
Yeah, what did we do
I,
exactly?
I did not remember, but
Why is this 2 cross 2? Or how could it be 2 cross 2?
Pooling?
No. Anybody?
Stride of 1.
No.
chain
No.
function.
Stride of not one, but
Actually,
right.
we did manipulated the chain differential equations and we got this.
No. I'm just asking you about the convolved output.
Stride of 2.
Very nice. Stride of 2. So in this case, instead of SH being 1, put SH to be 2. Right? So what happens here? So this becomes 2. So that's 2 by 2. That's seal of 1. Sorry, floor of 1. That's 1 plus 1. Then the size becomes 2. Right? So in that case, the same 5 plus 2 minus 3 by 2. So that's by 2. Okay. So the size is 2 plus 2. So see how the simple relationship interacts. You'll get an intuition very easily, right? So now you can do all sorts of things. So if they have a padding of 4, right, that is 4 on top, 4 on the bottom, let's say, and a stride of 3, 4, whatever it is, and if it's the image is the rectangular image, right, you would have to do it separately for the horizontal pixels and the vertical pixels, but the idea is the same. Any questions here? Yeah, people are okay. This should be quite straightforward, intuitive.
Any guideline for taking the number of kernels?
Come again, sorry.
Actually, in different architectures, they are
Mhm.
taking different kernel sizes.
Right. So if you
Number
come
of
back
kernels.
to this, right,
Yeah.
the number of kernels, I'll show you this because when we discussed 3D convolution, we talked a little bit about this and maybe not. So you remember this, right? So what did we say? So this is an image, correct? This is a image which has already three filters, R, G, and B. All right. And then the kernel should also be a three-dimensional kernel in that sense, right? So it should combine a red, green, and blue. And how does the convolution work in this case? For each of these kernels, you will have these kernels will be placed upon the image. You will get a single output. Correct? Yeah. So at the end of the day, what this kernel does is some sort of a weighted average on all these three different filters, right?
So single output means it will be on one
It,
dimension.
it'll reduce in one dimensionality, right? Like it'll go from three-dimensional to
Mm-hmm.
two-dimensional, right? In this case, right? Look at this. So this relationship you need to understand. So this right now the image is some n cross 3, right? The kernel is k cross 3, but the output image would be n cross 1. Let's say we did some padding and all that. Let's say, okay, right? So this you just get one feature map for this kernel. But let's say I have two such kernels, right? Now I'll have two feature maps, right? So you'll have n cross 2, right, where each corresponds to a specific feature map. And these feature maps could be anything. You can imagine this kernel was trained in such a way that it was able to extract the red part of the image. So that becomes this back or some weighted
That means
combination of.
like how many number of kernel groups,
Mhm.
that number of layers you will reproduce, right?
That number of layers you'll be producing. Very nice. Yeah, that's it. So in this case, you have two kernels. So you have a two-layer output.
Sir, is there any general intuition for like when you given
How
a
many
data set?
kernels do you want to use? That is very
Yeah.
architecture specific, right? Like if you have seen AlexNet or any sort of VGG net, they have a specific type of architecture. There is a reason behind it. Like for instance, if you are looking at human faces, for instance, right? Like you have ideas that at the lowest level you want to capture the edges of the face, the contours, the different combinations. So at that at that stage of the network, you might need to have many kernels, right, to extract different contours of the image. But then at the later stages, you don't have to have too many, because once you come to certain high level features where there's a combination of multiple contours to give you the nose, eyes, and stuff like that, then you don't have to have too many kernels. So that kind of reduces. And in fact, it again, right, that is this is very much empirical in some sense, that you have to figure these things out by practice, right, through practice. So I can't give you just one straightforward answer for this, unfortunately, right? But I can give you a thought that if there are many low level features that you are interested at the start of the image, then you might have to have many such kernels which could extract those low level features. But then later, as it goes up at the hierarchy, you want to maybe reduce the number of kernels that you are using to extract something more high level, right? That could be one way to think about it, but that's not always the way it will work. Sometimes, you might have in the middle layers of convolution a lot of such kernels, because such a mid-level features are more important to do, for instance, in that particular data set. So that might be uh, um, a good enough reason to do a different architecture there.
Sir, in general practice, like uh, after each convolutional network, we have a pooling layer, right?
Yeah.
So can we also have like can we take like both max and average pooling
Mm-hmm.
after each layer? Is is that like can we do that? Like is it
Um,
standard practice?
Standard practice is to fix a specific type of pooling, but I mean, nothing stops you from doing it. Is my take on it. Nothing stops you from doing both of them, right? If you think, okay, let's say if you think there are features in your data, that's it. Like you have to go back to your data again, right? You have to always think from the point of view of what do I want to extract from this, and what features do I think that if the network is able to extract from here will lead to better performance, right? You have that. Let's say you have certain smooth features of the image as well as certain contrasty features, which are both equally important, right? So maybe certain, at certain layers, you could do both max and mean pooling, right? Like both of them could be done. I have not seen a network which does that, or if I might be wrong. I don't know exactly this literature very vastly. Maybe if someone knows, they can shout it out. But as far as I've seen, people don't do that. But it's worth a try. You could try it and see. I don't know if the current uh, you know scripts out there allow you to do both simultaneously. Very likely they might be able to let you do that. But yeah, it's worth a try. You can do it. But again, it's not just that, okay, let me try it and see what happens. That sort of approach is always very bad. The approach should be motivated by your data. Like, what do you want at the end of the day, your objective to be from the data, right? Like, do you want the classification performance to improve? What features of your model will help you improve that in some way? And if you understand the basic intuition behind what max and mean pooling does, right? Like extracts more smoother features and or extracts more contrasty features, those things very important to you in terms of classifying the image or making some prediction about it, right? If that is the case, then yes, it makes sense to do that. But you should always have a rationale. You can't just go like, because that's what happens, right? Let me throw a deep network at this data and see what happens. If that is the attitude that people have when they're using these models, then they have lost the point behind the model itself, right? The point behind is to solve some objective. And if you understand your problem really well, like, and your data very well, then you will exactly know that this is the first approach to take, and then you will start seeing some improvements. That does not mean that people have not done exploratory stuff. That is, they have not people sometimes serendipitously have added certain things to the network which seem to have worked. But that's more often than not developed with years of intuition, right? Like, you work with your data, you work with the models, and you get like a feel for it. And finally, you know that, okay, maybe this will work. It's like how you would play chess again and again and again. You get this pattern recognition formed, and sometimes you play a move just through intuition, right? Like, you don't have to think about it. The same idea, right? If you practice and understand these models deeply in some sense, you can then make some inferences.
Sir,
Yeah.
one small doubt.
Mhm.
When you convolve the three layers, the
Yeah.
output of each layers are added together?
You mean to say these two?
No, no, three filters. Very basic actually. No, no.
Oh,
When you
this
apply
these
with,
ones?
yeah,
You mean the one previously? You mean here in this
yes,
case?
yes, they are
Yeah, yeah, yeah.
added.
When you convolve, you add it, right? So you
Okay.
multiply this with this, and then this with this, and so on and so forth, and then add it, right? It's again the dot product, but in the three dimensions. Exactly how you do in two dimensions, you do in three dimensions. All right. Any other questions people want?
Sir, so
Yeah.
how does this become single layer, like single?
You mean to say how
Yes,
does the
yes,
dimensionality reduce here,
yes.
right? So wait, did I mean, it's so in the sense that when you take the dot product, right, or you basically take, so these are sort of like your weights, right? These are sort of like your activations. And then when you do w1 a1 plus w2 a2 plus dot till wn right? So which is probably here. So then you get just a single output. So when you convolve with a three-dimensional kernel, you get a single output, because the output of a dot product is always a scalar, right? Yeah. So you just get one output. Is always some scalar s. So that's what you get here.
So for single channels, it should be single outputs. No, I mean for the
You
first.
mean to say you a single channel here? No, 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 no. For a three, so that's what I'm trying to say, right? When you have a three-dimensional input, you have a three-dimensional kernel. But if you want only this part of the kernel to be averaged out, you have to set these two to be zeros, for instance, right? But the math works out that way, right? You can't change the dimensionality of the kernel, right? You can't just individually just multiply this and have three layers. That's a different operation. That's not the dot product. The dot product is when you take all this, multiply with the individual pixels and add it up. That's the dot product. Because if you do this individually, you're not getting a single output. You are getting a 3x1 output, right? One for each of these layers, right? So then you'll have another layer behind and another layer behind. So that's not how dot product works, right? That's not how convolution works.
Okay. Oh, so I was actually taking these as separate
No, 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 no.
vectors
This
actually.
is the
Okay, this is
scenario
single
where
vector.
there are separate kernels, right?
Right,
You have
understood.
two three-dimensional kernels, and then you will get a two-layered output.
Right. Okay.
Got it? Yeah. Any other questions from any other part, not just CNNs?
Sir,
I
there
had
is
a very small question, sir,
Yeah.
regarding the calculation that we are doing in the previous slide.
In
Yeah,
the let's
yeah,
see
that,
the kernel size, right?
yeah.
Which
So
one?
I was wondering, like, how did we get two up there? Like, it was 5 plus
Yeah, yeah.
3 plus 5 plus
Okay.
2 minus 3, right?
Yeah,
7 minus 3.
five plus not two, two into zero. Okay, I always do
Oh,
this. I put dot as multiplication.
oh,
Two times zero. 2p, right? Two times. Okay. Now is that clear?
yes, sir.
Okay, cool. Yeah. So try this out, guys, with your own data set. You had the Caltech data set, right? Like the objects data set as your assignment problem. You can just apply the same things along with the kernels and see if the size works out, right? So it's a very simple relationship.
Sir, I have a question. If the
Mm-hmm.
input image is like a rectangular image, then how
Mm-hmm.
can we
Mm-hmm.
take the padding?
So padding there is again could be symmetric, but it depends now on the size. So let's take the size. Okay, that's a good question. Let's take the image are rectangular, right? So in your case, probably it is longer in the number of columns are bigger than the rows, right? So let's take the image to be 5x10 instead of 5x10. All right. So in that same thing, let's take this scenario. Let's take maybe I'll erase some part of it, these parts. Okay. So let's take the image size to be 5x10. Let's take the kernel size to be the same thing cross it, and let's take a padding of 1. That is, you have one layer of padding around. That is, if this is your image, you have one layer of padding around. Okay. So let's say we zero pad it, right? Okay, we're zero padding it. All right, got it? Yeah, so one layer of padding around, and we are taking a stride along the horizontal. I mean, for simplicity, I'll not call it horizontal, and let's call it rows and columns. Okay, it's much more easier that way. I don't like this terminology. Let's call this SR. I'm taking a stride of 2 in the rows, and in the columns, I'm taking a stride of 1. Okay. Yeah, so these are my rows, these are my columns. Now tell me how the output kernel will look like, right? So my WR would be, people can calculate this on their own too if you're wishing to do that. So that'll be 5. So maybe people can calculate it for a minute and then I'll do it. So
I think, sir, this is 3, right? 5 plus 2 into
Yeah, 5 plus 2 times
1
padding is 1, right? Minus your
minus
kernel side
3,
is 3
3
divided by
2.
the this
2
thing is 2, right? So plus 1.
plus
So
1.
that is 5 minus 5 plus
5
2,
plus
7
7
minus
minus 3,
3, which
4.
is what? 4. 4 by 2
4 by
is 2. So that
2.
is 2.
3. Total answer.
Yeah. So 3. Okay. So you'll get a 3 rows. Now tell me about the columns.
We will put only one thing will change, right? SC, right?
Sorry, come again.
In this formula, only SR will replace to SC, right?
Yeah.
Because 5 5.
Yeah.
Then
Then it will be 10.
By 10.
it's no.
No.
4
Do
5,
it
sir.
again. 5. Let's do it. WC is you have your input image, which is 10, right? 10 pixels in the column
10
wise,
plus
plus 2 times 1 padding minus the kernel
minus
size
3.
3 by 1, right? Plus 1. So that's what? So 10
Then
plus 2, 12 minus 3, which is
9,
9 plus 1,
10.
10. Right? So the input image is going to be 3 cross 10, right? And that makes sense, right? Because you do not take any stride on the column, right? And then you have a padding. That means you will get the original image size back, right? We'll get the same size as the original image. So that's why I get 10 here. But here we took a stride of 2 along the rows. So that reduced in dimensionality. So that became 3 times 10. Okay. So hopefully that answers the question that was posed, right? Like if it's a rectangular image, then you just do individually for the columns and rows. And this is how even the PyTorch does it in its backend code.
One question, sir. Can
So
we
yeah,
take the kernel as rectangular?
yeah, of course. Then what happens is this K would be either KR or KC, right? So instead of having a 3 cross 3 kernel, you could have a 3 cross 4 kernel, right? And now if you apply, it will be the same thing. But this time you replace the K value with the rows of the kernel or the columns of the kernel, and it will work out the same. So a rectangular kernel will also be helpful. Will work. You'll see this formula working. You can try it out. Okay. Any other questions people had about feed
Are there
In our
forward?
are there any
sorry,
cases where my output is bigger than the input images? Like for example, if I want to do or build a network for resolution of images or something like that.
That's a very nice question. Yeah, possibly. Yeah, let's say let's take if my padding isn't 1, right? If I take a bigger padding, right? I take a padding of 4. Yeah? Apply it on the same thing, you will get a bigger size of the image, right? But again, you have to see what the padding means here, right? Like you could pad it along the sides by so making the image circular. You remember we had different types of padding. Zero padding is the most common, but the circular padding, there is mirror padding, that is you just mirror the image on top, on the side, and that way you can increase the output feature map size. But are you increasing the amount of information? I don't know. So your question was if you want to increase the resolution, right?
Yeah.
Maybe there is other ways to do it. Like there are ways in which you could split pixels, right? Even within the image, there are ways in which this pixel could be projected onto, sort of scale up the image in some way. I don't know if those are possible, at least in the architecture that we have, because we always try and reduce the dimensionality in a CNN. But I mean, you could do some pre-processing of the data and then you can scale it up or down, right? But typically, you want to scale down, right? Like the point is, if you do any sort of interpolation of the nearby pixels, right? Like you increase the size of the image and then interpolate nearby pixels, you are just creating some redundant information which probably you don't need. But it could be possible. Okay, so I could give you another way to do this. Another way to do it would be, you first do a convolutional layer, that is, you do a series of convolution layers, right? Go till like a space where you get an abstract. Now you start deconvolving, but when you deconvolve, you can deconvolve it to a resolution higher than that of the input size that you get, right? So you do a DCNN, deconvolutions. Okay, and then when you bring the image back up, you do it, you increase the resolution of the image in this way, right? And you go the other direction. Now you'll have hopefully a higher resolution image than that you started off with certain features that are highlighted. This is a possibility, yes. So you go from here to some abstract level using a CNN, and then you use a deconvolutional neural network and to deconvolve this back, and that could be of a bigger size than that of the initial starting image.
Uh, Sir, image, I mean, image resolution is fine, and a lot of work has been done. When it comes to video resolution,
Yeah.
the one thing is that the easiest thing that people have tried in the past, that they have, you know, uh, went on the image resolutions, path, like
Uh-huh.
they have created frames out of videos and then
Yeah.
they have,
Yeah.
done that. But in that, what the missing factor is the relationship between frames to frames.
Yeah. Yeah. Yeah.
Is there anything done to, find that relation
Improve that.
between the changing frame?
Good point. Let me think about it. So if you think about RNNs, for instance, right? Like those are very nice temporal models that you can use. And let's say you have like a 30 frames per second video, right? And you want to make it 60 frames per second, and you want to, and there are many approaches that people have used to do that, right? Like in some cases you have used um, frame interpolations and all that to kind of improve the quality of the image, but still should maintain this temporal coherence across the video. So one way could be that, if you remember how we were looking at RNNs with attention, right? Where we were trying to uh, look at what is the sequence content of the image, right? Like if you use some form of an encoder decoder architecture where it's an auto encoder, for instance, right? Like you encode information about the video and then you start decoding the same information out, but this time with higher resolution, or sorry, higher frame rates. And for that, what should happen at the output is that you should be able to more frequently sample from the decoder than you do it from the encoder space, right? Let's take this case. Let's go back to that. That's a nice point that you brought up. Maybe we'll. So let's take this to be the case, right? Now here what's happening is, at every time step of the encoder, you have a decoder, right? And you don't have others, let's say many such steps, or decoder steps that are more in number compared to the encoder ones, right? Let's say you gave here frame 1, frame 2, frame 3, and then you are decoding out frame 1, frame 2, frame 3, right? Let's say instead of decoding out and sending, you could probably have more steps of decoding here, right? Intermediate steps, right? And you get f1 prime, f2 prime, f3 prime, and so on, right? And that way you have now doubled the amount of frames that you have, right? And since this will embed information about the sequence as well, because that's available in the hidden states, this is one possible way in which you could improve, right? and I think people have tried this before, and I don't know how well it works, but there is some literature on this,
Question
right?
is, why do we increase the frame size actually? Number of frames.
The image, sorry, the video frame rate, if it improves, right, like then you get a very smoother,
No,
uh,
sir. Actually, there are a lot of limitations on the number of frames per second. There is
hmm,
a formula for that one that
hmm.
should not exceed the natural
Correct.
frequency of the electricity. So,
Absolutely. Yeah.
yeah,
Obviously, you can't increase from the Nyquist rate, right?
yeah, Nyquist rate. Yeah, yes. That's one point. And for video pictures, our retina also cannot cope up with that kind of high
Mm.
resolution. I mean, high Nyquist rate.
Exactly, but I'm talking about images that are very low in frame rates, and there is some temporal relationship, right? Like for example, if you look at these old school videos, right, like where have these black and white images back in the 1950s, where Charlie
Slow
Chaplin and
movement.
all,
Yeah,
yeah,
yeah, yeah.
yeah. So those could be integrated to seamlessly give you an experience, and people have done this. I saw this in like there's a YouTube channel called 2 Minute Papers, right, by if you have somebody has subscribed to it, it's a very nice channel. Like I would recommend it. 2 Minute Papers by Karoj Rolai Fahir. Right, so you should check it out. He puts a lot of stuff out there, which is very recent. So it covers it in 2 minutes, or not 2 minutes, but roughly in around that time. But it's interesting. You should check this out. I saw a application of this a while back, but yes, those are all valid points. Any other questions? Still have 15 minutes or so.
Sir, in our syllabus, do we have AlexNet and some other VGG and LeanNet, some different types of
Uh,
uh,
in, uh, in
in our syllabus? Do we
in
have
the
those?
syllabus, so in the syllabus, there is only CNNs. I mean, obviously, we could cover a lot about it. It's not that we can cover about AlexNet. I mean, if you want, we could have a class on it. Maybe later, once sometime in the middle of Crackle 2, I can give you some pointers on it, and we can have a quick discussion on the different types of nets. Because I remember I post this paper, right, the survey paper that has a bit of information on these things. Yeah. So yeah. So we could look at AlexNet, VGGNet, ResNet. Inception is one nice thing by Google very recently, not too recently, 2017, in the AI, modern AI sort of spaces like history, right? Like people. So there's lots of structures like that. So maybe we can do that. Yeah. Sometime in the middle, if we get some time, I'll go over these things with you. We can have a discussion for sure.
Sir, one thing I want to ask from
Yeah.
personal perspective. I mean,
Yeah.
we have been building all these CNNs based on the
Hmm.
libraries that we have been provided, and over the years
Hmm.
we have done this also.
Yeah.
So, do you think writing those libraries or from the scratch would help us in any way? I'm
Oh,
just
yeah,
asking.
that's a very nice suggestion. So, at least speaking from my own experience, so I did a lot of reinforcement learning models when I was doing my PhD, right? So, at that time, I wasn't very familiar with the ideas behind machine learning, and so I was learning it. And coding from scratch helped, right? So, it's a balance between, do you want to reinvent the wheel or do you want to understand stuff, right? So reinventing the wheel in some ways helps you get a better grounding, and I would urge you to do that. But do it for simpler problems. Don't do it for like really complex ones unless the motivation is to actually build those libraries in the first place. But coding from scratch helps a lot, is my experience about it. Right? You kind of take a problem and then you start from the ground up and you build the entire thing. Then that's amazing. That feels like really good, and also you get a lot of understanding from that, right? So um, it depends upon what is the problem at hand that you are trying to solve. Is it more like it's done for the purpose of learning? Then take some simple problems, right? Like even a simple backpropagation that we were looking at, right, in CNNs, right? If you were able to implement this for a single layer, right, that will give you a very nice feel for it, right? If you code this, let's say. And then if it starts working, you'll know, okay, this is how it works, but on a grander scale I can see that, right? But then writing code which is optimized, which can sort of scale up for different layers and levels, that requires a little bit more like a team effort, right? Like many people have to work on it. But um, getting a bit of an idea at this level, right, like doing one stage at a time, and figuring out, just have a one layer CNN, and then do like a fully dense layer after that, and you code this entirely from scratch. Of course you'll get a lot of understanding of what's happening. I'm pretty sure about it. But if that's the motivation, just keep it at that level. Yeah, you don't have to uh, reinvent, but you need to understand what's going on inside there. That's definitely there, right? But I get the fact that sometimes it's a black box most of the times, right? You don't see the back end stuff. It's hard to get a good feel for it. So in that way, for sure. Yeah, yeah. That would be my advice on
Also, in the
that.
yeah, thank you so much. One more thing, as we know, the CNN has is
Yeah.
extracting features in the middle layers, and those features can be very minute. So, is there a way to see
Hey, sorry, I'm
what are the
losing your.
features they are trying to
Sorry, I
extract
lost
in
your
the
voice there. Could you
intermediate layer,
repeat it?
hidden layers?
Your just voice got broken up. Yeah, yeah, yeah.
Can you hear me now? Hello.
Mm-hmm.
So, as we know, the CNN is
Yes,
extracting deeper
yes,
features, like very, small
yes,
features,
yes.
and it extract those features in the
Yeah.
consecutive layers, and then of course we use it as per our needs.
Yes.
So my question is it possible to see what kind of features is it extracting in the middle layers?
Yeah. So I'll
Is
give you
there
an
any
example.
library
Yeah.
for that?
To do that, actually, papers help you get an intuition about it. Like even the deep learning paper that I sent you, Lecun, right? Like you can see in that Lecun's paper, there are these intermediate layers. But there isn't a library as such. But that's why I wanted you to do this in the assignment. But this is how I would see. This is from a CNN basically. Okay, the CNN is trained on face data or faces, human faces. Yeah. So low level features look like this, right? Like these look like extracting contours. These are extracting orientations, lines of different orientations, and so on. Okay, and then at the more mid-level features, you can see features like nose, eyes, the eyebrows, the forehead, and many others, right? You can see that. And at the highest level, you can see faces emerging and have different templates for them, right? And this is how you will visualize them. How can you visualize these are nothing but the weight kernels, right? So the weights
Right.
look like this, right, for each of those layers, right? At the highest layers you see these many kernels have been or you can see when you pass the input, this is how the kernel responds to that, right? This is how the weight vectors are there. And you can see that, right? You can visualize that. And in the intermediate layers as well, you can see that. So
I
many
think,
objects. Yeah, yeah.
so just to add to your point, I think we don't need a library. Just like after getting the
Training.
output, we can just collect it and plot
Yeah,
it simply.
yeah, exactly. That's what. So it depends, right? How the problem gets solved. The the weights, the kernels will look like this, right? So you can just plot them and then have a look at it. So you'll
Okay.
get these features out. And that's the interesting part of it, to visualize this, because that tells you, that'll give you a much better understanding of what's happening, right? Like the object data set, you will have an understanding what are these mid-level features that are being extracted, that's helping you classify the image, right? So
Okay. Answer one request from our side.
mhm.
This September 18 is the deadline
Yeah,
for the assignment,
yeah.
but we are having exams from
I
21.
understand. Yeah, no, no. I just gave that as an initial deadline. I knew that there'll be extensions. I'll extend it over.
Thank you, sir.
Okay. Any other thing, guys? Yeah, I think we can wrap it up here, or if there are other questions, I'm happy to take it.
Sir, what is I was going through one document, but I was not able to understand about the dying activation function.
Mm-hmm. Sorry, what activation function?
I mean, there was one topic called dying activation function.
Spell it. D-I-N-G?
DYING,
D-Y,
dying.
dying activation function. Okay, cool. That's a nice concept. So let's take for an instance. How do I explain this? Okay, so let's take a ReLU function. Okay. Should I? Okay, let's take that. So that's a ReLU, right? Now, is this a static function or a dynamic function? That is when I say uh, y equals f of x, right? And I define y to be 0 for x less than or equal to 0 and 1 for x greater than 0, right? So that's a value, right? Now, my point is this a static function or a dynamic function?
Dynamic functions, sir.
Why?
Because it changes as per the output.
No,
It's
not
giving
that.
you the values, right? For
Yeah,
each input, it's giving you a different value.
yeah.
It's
So it's
not
not.
static. Like,
It's,
but in the left part, we can say it is static because it's not giving any value, same value for all the inputs.
exactly. So the point is, this is not a dynamic function, it's static function because there is no dependency on time. Okay, there's no x comma t here. All right,
No, it,
or as in there's no way in so or in other ways, I do not have an expression of the change in y or y dot, right, as a function of x, right? Right. So the activation function here in some sense is not dynamic, right? Right, it's just that it's taking the input x and then passing it out to an output based upon this function, right? Now let's say I have a function which is y dot, if I say change in y is minus some uh, constant plus f of x, right? Right. So let's take this to be the case, right? I have some change in y as some function. So if the function f of x is 0, then uh, at steady state y will approach k minus k, for instance, right? So that means if you look at the dynamics of y dot as a function of say time t, right? If I give no input, then it'll just decay off, right? Right, the idea that you will there is a function that's evolving across time y. When you take the solution y, not y dot, sorry, when you take the solution y as a function of time, it will decay. Now if f of x is like one pulse that's happening across a short period of time, x comma t, then the dynamics of y of t will change depending upon that. So this is a first order equation where the solution is e power minus k into t. It depends upon f of x, but I believe it's some form of e power kt is the solution, right? So it will just decay off. And if this is a pulsed input, then it'll increase first and then it'll decay off, right? So there are expressions of the activation function that you can have that can change across time, right? So when people say it's a dying activation function, then you can change the values of y as a function of time also, right? Like how it could behave. That could also be a way in which you can modulate some of the input function. There are many uses for it. If I remember, one of the major use could be to improve sparsity, right? Like something that is not too high of an input might not be able to excite y enough, so it will just decay off. Something that's really high, then it'll be able to excite y, or the y will be substantially high in order to affect the next layers. Right? It might be tricky to train these things, but I guess that's the idea behind a dying value function, or sorry, dying activation function. So there are many ways to interpret that. One of them is like this. So Anything else? Cool. Okay, guys, then I think it's 11:15. Then we'll stop here. Yeah, hopefully that cleared up some of the questions that you had, and we'll quickly discuss in the future about the different types of CNNs also once you get some time. But otherwise, all the best for next week. Stop the
For
recording.
the exam, those different types of CNNs is not there, right, sir?
No, no, no,
Okay, sir.
no. We didn't even discuss it. I'm not going to question it.
Yes,
Okay.
thank you.